Hello?
Yes, we are here.
I did see it. I don't currently see your shared screen.
Mhm. I'm not really sure how, let's see here. I
Down
must
the
have done
screen, you have a green icon, screen sharing, no?
well, it would appear that I do not.
Bring the mouse at the bottom of the screen and the line is showing up. Unless you are not the owner, so you should be validated by the owner of the session.
So it worked for a little while. Huh? Let me see here. Well, unfortunate. Let me try again. Sarah, do I have proper authority to do this?
Yes, as a co-host, you should be able to share your screen. If you, yes, it's sharing now. So
Okay, awesome. So I guess what I need to do is get rid of things like this that are
Okay, we see
probably in the
it.
way.
We see your assembler code.
Oh, whoops.
I see a mistake somewhere.
You see what?
It's
There you go.
a joke. It's a joke. Okay.
All right, I've got some processes running. I'll just go ahead and get rid of these. Sorry about that. I don't know what happened. Hello, everyone. I've got a couple of sites I'd like to introduce to you guys. One of the questions that we seem to be getting a lot from people are just from the other meeting. Here we go. Servos, motors, advantages and disadvantages. And I was sort of asked to put some slides together on this subject because I know people are a little confused as to when to use servos, when to use steppers, when to use brushless motors, and when to use linear actuators. This is a site that I found last night. I went out looking, and it's from what's called RealPars, RealPars.com. And these guys, I think, do a fairly nice job of describing some of this information. But a lot of the times you kind of just have to have a discussion like we're having now to really determine what you're going to use in your project. Servo motors typically, I mean, let's face it, they can be extraordinarily large and very powerful, but their practicality is always in question when we're doing what we're doing because of the power utilization and also the amount of torque that these devices can really deal with. People don't really understand most of these microservers, you know, that we use in the hands as such. Very small, and they're very small, but they still use, in my opinion, an awful lot of power because they're constantly being pinged. You'll always notice that when you're using servos, there's always like a warble. They're moving back and forth like 1 degree of freedom constantly just to make sure they have their spot. It's sort of an oscillation, but that's not a problem except that it helps you to understand they're constantly using power. We have really gotten away from servos quite a bit because of the power curve. The fact that they have to be energized almost all the time. It doesn't work out well for us. When we're not using the power in the arm, we want to shut the power off and conserve, because you know your battery is of course your biggest asset when you're building bionics. So we've switched most of our development over to brushless motors. Not only are they a lot more powerful, but you know, when you park them, they're parked, they're locked. and they require no energy whatsoever. You do not have to energize them once you park them. What I wanted to just real quickly, just kind of buzz through this this website. I would highly encourage you guys to go here and take a look, because I think they've done a very nice job of identifying the different types of motors, whether it's a servo or whether it's a linear actuator. Linear actuators, of course, are much more powerful, typically, because the gear ratios are there. They're usually a little larger. We have a couple of devices here that use linear actuators on the hands, because they have a lot more lift, rather than the servos, which basically you're dealing in ounces. Linear actuators, you typically, even with the smaller ones, you can get pound torque out of them, a lot of power. Not probably as much as we're getting with our motors, because just because of the size differential. But linear actuators are extraordinarily good, but they're also a little on the expensive side. The linear actuators that we're using, we have bought some from Atronics, but we also print our own if needed. And we do use them, say, in higher power, like elbow joints or shoulder joints. Linear actuators make a lot of sense. In fingers, not so much. It can be done, and there's some people out there that we see doing it, but they seem to have limited success, because even if you can get the thing to fit, the power requirements are still there, the expense is still there, and we have avoided both. We don't like to strap a lot of battery power on humans. But if you just kind of browse through this site, I think it will answer a lot of your questions on these different types of devices. There's also some really, really good calculators out there. And in the event that you're using whatever technology it is that you decide you want to use, be it linear actuators, servos, steppers, some of these calculators can be extraordinarily helpful, because they will level set your expectations. They'll tell you really, what is my torque, what is my lift, what would I actually be able to move with this device. We have some people out there that have said, well, we use the full 360 servos because that way we can run them all the way around like a loop, and then we don't have some of those issues. But at the same time, they tend to run in the end, they tend to run into the same issues that a lot of other folks have. This particular device, of course, uses servos. We have another one here that we were asked to build. I put a table over here full of toys. This is a little show and tell table we put together, but this is one that we use to test our programming. This one doesn't really care whether it's Arduino, doesn't really care if it's a Tinker board or a microbit board. We use this to test basically our code from whatever platform we're working with at the time. I'm just going to hook a little battery pack up to it, do just a quick demo, because everybody just loves to see this thing go.
Rick, could you replace the screen, your screen by the camera, because you are just like a stamp on the screen.
I am?
Yeah.
Okay, let me see if I can do that.
You have to swap the share my screen with your camera, please.
Okay. Stop share. How's
yes.
that?
Yes. Okay.
Okay.
Show us.
So basically, this is just a small device that we use for testing purposes. And as you can see, each individual finger, each individual joint is a servo mechanism. The thumb, of course, can swivel. Oops. It has a swivel thumb that can swivel this way or open and close this way. This is kind of a fun device because it's just sort of standalone to where you can test code, you can test out basically what you're doing. However, this one has helicopter parts, and only one servo for finger. Whereas this one has actually 15 servos, which would be 2 servos for finger, a wrist, multiple for the thumb, and of course the swivels. Now, I have to tell you, these servos take a lot of power. If you're driving 15 servos, you need some amperage, and it's incredibly impractical. So a lot of what we're doing now, we're doing with brushless motors, because we can replace multiple servos with a single brushless motor, and we can generate an enormous amount of power on the fingers. However, you don't necessarily get individual, by using a single high-powered motor, you don't necessarily get an individual control of each finger. But every time you add a motor, of course, you're increasing your amperage that you're going to be using. What we have tried doing in the past is we index through the motors, where at any given time, only one motor will be operating. And it's like cyclical, to where it goes and it moves each motor individually. That way you're only at any one given time driving a single motor from your battery. That does save battery power, but it's kind of herky-jerky. And a lot of the people that we work with that like our Bionics tend to say that they really want practicality first. The more complicated it gets, the less they can trust it, more things to go wrong. Servos also have a very short life. Some of these servo units we have here, we're real lucky if we really use them. We're lucky to get a day. And you know, like the SG90s, for instance, they have metal gears, but the little motors, they just burn out. They don't have a lot of longevity. However, you can buy a bag of them. You know, the beauty is you can buy a bag of these for about $11. So it's not that they're particularly expensive, but people don't really want to, they really don't want to do a lot of maintenance, you know, on their devices. They just want them to work. We've had very good luck with just using brushless motors, because we kind of tend to take them out of broken cordless screwdrivers. They have a lot of torque. They've already got they've got a great little gearbox in them. They run usually around 3.5 volts. And quite frankly, they really do the job. I know Sarah's seen this before. I hate to keep doing this, but we have right here one of the devices that goes in a Bionic. This is the entire thing right here. This is the brain, the battery, the charger, everything, all in one. This is the charger unit. So the battery, the power, everything. This basically goes in the cuff. And if we were to hook this up very quickly. I hate to stall you guys, but I got to go with it. Let's see here. Let's just give it some power. There we go. Isn't that just awesome? Here we go. So basically, I don't know if you can see this thing turning, but when I tilt the mechanism to the left, the motor goes to the left. When I tilt it to the right, it goes to the right, and it goes at whatever speed I tilt it. We call this index gyroscopics because everything's done by a gyro. Now, if you move your arm to some odd angle, it resets. So now it's all reset. So when I turn it, it now knows my plane. Now, this thing is so strong, I cannot physically turn this with my hand. This is basically a screwdriver motor. This guy here is what handles all the gyroscopics. We've had enormously good luck with this because it's super simple, it's super small. This battery will last pretty much all day, depending upon use. And it plugs into almost all of the e-NABLE cuffs. So you have your right and your left, okay, and your speed just by how fast, how much you tilt. And what this allows us to do is to open and close the hand, okay, based on one motor. And the clamping power on this is incredible. It's incredibly strong. So there are a lot of workarounds on these different types of builds and ways to build your Bionic to where not only, you know, you're not really making a lot of compromises as far as strength versus the amount of strength that you have versus the complexity versus the power utilization curves that you need. We are now building that one into, my show and tell hands are all stuck together by cables here. We're building that into this hand. Okay, this one is going to be a proud recipient of that, of that box. And we're also going to be putting it into this hand that now has our new finger technology on it that uses the bicycle chain technology. These fingers can actually be attached to any e-NABLE hand. And we've since rebuilt these fingers to where now they no longer need the springs that you see on the fingers. So these things are incredibly strong. The tensile strength on these fingers is 2,200 pounds. Made out of bicycle chain, so it's really, really cheap to do. And this is really awesome for people who don't have a lot of access to 3D printing capabilities. And we right now are using this for underwater, you know, underwater usage, divers, things of that nature that need an enormous amount of power, enormous amount of torque, and longevity. But these things are super, super strong. That it's just a test one and it's broken at this point, but I just thought you'd want to see it. Let's see.
Rick, sorry, when you say we, who is we?
We build, we have our own little lab here.
It's a private labs, or it's is your discovery available for e-NABLE people?
I work with e-NABLE, and anything we do is open to anybody at e-NABLE.
Great.
It's all open source.
Great. Okay.
It's called Cybernetic Design Solutions, and we have been building these things for about 6 years now. It's just sometimes we take a different trajectory on the way we solve problems. And what we're trying to do now is we're trying to take all of our builds, this type of technology, and make it compatible with existing e-NABLE technology. Because it makes sense to do that. People have spent an awful lot of time and a lot of effort, you know, designing some of these e-NABLE hands. What would make sense is be able to look at these in a modular fashion and snap them right into what is already there and already existing. And I believe that makes a lot of sense because the e-NABLE hands cover a wide spectrum of problems that an individual may have. You know, they may have lost below or above the elbow. They may have lost the wrist down. They may have partials. So it doesn't make sense to discard all that hard work. But if we can augment it and we can make modules that make it better or maybe more versatile, sometimes that makes a lot of sense.
Okay. I will touch base with you because you make a lot of discovery that can help us. Just for you to see that we in France we are working alone, but we already have some achievements, and we are using some Actionics motor and so on. But I like your the chain fingers.
The fingers are remarkably strong.
Yeah.
And what I wanted to do, if you don't mind, I don't want to hold this up, but I'd like to show you basically how they work. The fingers, as you can see now, we don't use the springs anymore. The springs are no more. That's no longer necessary. This is an early model, but you can see how much control you have over this. It's like
Great.
an octopus. These springs, we have a new model that these are no longer necessary. These all go away. So this is the old model I just have sitting here so you can see it. But when you're talking about a bicycle chain like this that has that level of tensile strength, 2,200 pounds, and then it's tendon driven, which is really a good thing. People say tendon driven is bad. I really don't think that's true. I mean, we're tendon driven, people are, right? So it can't be all bad. These fingers we are attaching to all of the e-NABLE devices that we're putting out there. Of course, we try to cover them with something that doesn't scare the kids, but they actually look quite good. We're also using, just so you know, I see that I'm familiar with the hand you held up. We're also using these for transmissions.
What?
This is basically the transmission that's in it. So what we can do is, it's like these are used for remote control cars, right? So it's a complete, like a transaxle transmission. And when you turn this, this can continue, much like in the Whipple tree, without, think of it like a posi track in a car.
There's a differential system.
Yes, it is.
If you block on the right, it turns on the left.
Yeah. And,
Okay.
and quite frankly, these are nice because they cost about $6. They're very inexpensive and they have metal gears. I'm trying to hold it up in front of the camera so you can get a look, but they use them in remote control cars quite effectively. And that's another thing we tend to do is if we can buy something off the shelf for $6, rather than have to 3D print it, it saves us a lot of time and money.
About the chain fingers, all the components can be done by makers, or you have to buy something special? The metal.
No, you don't.
No?
No, you can make these. You can make these at home in about an hour.
The metal parts, where the metal parts are coming from?
Well, let me bring one out here, and I'll.
No, but you just explain. No, it's not the time now. Maybe you have other things to explain. But I'm so curious that.
That actually, all we've done is we've taken a bicycle chain, and we've reconfigured it. We've soldered, okay, to link certain components so they don't bend, right? Like these don't bend. So that means they are a vector, and some of them do bend, right? And then what you do is basically you do a stop end. We're using copper now, not on this version. This is the old spring version, but it's all done by soldering specific joints in a specific configuration. And what that allows you to do, okay, is some of these bend and some of them do not. So with a soldering gun, and we're using, you know, the industrial S50 staples from a big staple gun. You put these on. That's what we use to encapsulate the tendons and things of that nature. We also use guitar strings because they can take about a ton of strength in the tendons, and it'll basically allows you to configure a standard plain old bicycle chain into these with a soldering gun.
Okay, this is good. Just give ideas, right? Good.
And what we like about it is we can create them super fast. It takes about an hour to create a finger. My printer, I can't create a finger in an hour with my 3D printer. It takes me a lot longer than that. Typically what breaks the most on the hands that we send out are the fingers. These don't break. They're very, very strong. They don't rust. They have built-in roller bearings. Okay, so there's bearings built in. It's super cheap. It costs about $20 for 30 feet of this stuff. So if all you need is a soldering gun, in our case, we use number 9 wire, or we use staples, and we solder them in there to configure it so it bends the proper way when you pull the tendon. And,
All this is, sorry, yeah. Okay.
And
all this is documented. all this is documented, but just if you want to try to take your technology, we can easily understand how to do it and so on, or we have to exchange mails in the future.
Unfortunately, we haven't documented it because it's relatively new. We just released, we haven't even released the new version yet. When the new version comes out that doesn't have the springs are sort of an Achilles heel because they're in the way. And, you know, a person could catch them on things and bend them. We've gotten rid of that. The springs are no more. So now they're rock solid. And what we're considering doing is what we want to do is a video, which might make sense where we just build one and do a video and then share it with all of you so you can learn to do it yourself. But
if there is no spring, how the finger is going back to the extended position?
The finger, the way our bionics work is our fingers are on a loop. So when the motor's running, okay, the motor will, if it's going clockwise, just as an example, the finger will close. When it's going clockwise, counterclockwise, the finger will open and then there's a stop. It can't go past this point. And the reason we do that is because, like a servo, if you go beyond what servo has been told it's allowed to do, it'll break the servo. Almost immediately it'll burn it up. Making the loop, okay, that isn't going to happen because then you can actually control, like you would on your 3D printer with the belts, you can actually control that and say, well, if I get to a point where I'm going to break, I'll just slip. Okay, it'll keep where it's at, but it'll say, I can't go anymore. I've grabbed a hold of something and rather than break, I'll slip. And that's all okay. So then when the motor releases, everybody will go back to their original spot. And it works a lot better than it sounds. It sounds crazy, but it allows you not to have all the electronics that you would need to monitor each finger to make sure you're not going to break that servo or that particular drive on that finger when it comes to a stop. The stop is really important because if you go beyond what the finger can do, or you grab something and the finger tries to keep going, it's either something's either going to break or it's going to stall the engine, or say if it's on a whipple tree, you know, something's got to give. But by doing a loop, okay, the finger will open and close based on the direction of the motor. And if it gets too far, that individual finger will just slip. So each finger is on a loop. So one finger can stop on a whipple tree or not, it's up to you. And when that finger gets to the point where it's done as much work as it can, which we control with a large spring, so we can set the tension. So we actually set how much strength that finger can exert before it starts to slip, right? Much the same way your 3D printer does with the stepper motors to move the gantry. It makes it so much more simple, you know, from the build perspective. So now you don't have to have all those controlling mechanisms built in to the motors for protection. A lot of these machines, they'll use pressure. They'll say, well, if it hits this pressure, you know, then I'll shut that motor down, or I'll shut. Well, how are you supposed to do that? Over time, they tend to fail. Things don't work quite right, and they'll tear themselves apart. The slippage is totally mechanical.
Yeah, we were planning to add some sensor at the end of the finger, which is
and that can work for a while. The problem we have had is these things get wet. There's humidity. There's all these things, and the sensors fail. Now, if those sensors fail, your hand's going to rip itself apart if the motor's strong enough, or it's going to damage the motors. I mean, we've done it both ways. I'm not saying it's wrong. I'm just saying you have to build in a lot of fail safes that you can resolve very quickly just by using a slip.
Okay.
And I know how that sounds because it sounds too simple.
So it's interesting. We're going to look deeper in your stuff. We started in this model here. So we are using Actionics motors with position position control.
Right.
So we skip the issue of going too far and to break the motors. Okay.
But here's the problem, okay? Is it a servo or is it a stepper? Whatever it is, you have to apply power to it all the time.
Well, this linear motor is a screw
Yeah.
in a rod, right? And we make some measurement to check the counter. I don't know the English word. The counter. When you pull the motor, the motor is not running. How do we call this? The feedback. Okay. So we understand. We measure that it was acceptable, and it is not going to. We can rely on not energizing the motor.
Right.
So.
So you're using an actuator.
Sorry.
You're using it as an actuator. Linear actuator.
This one.
Yeah.
Yeah.
And that's fine. But you have to build your fail-safe.
The issue I have is it costs close to $100.
Yep. The linear actuators, the Atronics linears are very nice. They're very nice, but they're about $70 US each.
Yeah,
And,
in France it's called 90 something euros.
Yeah. So basically,
here,
that it's too expensive for us, and so we 3D print our own actuators if we need an actuator.
Small like this?
Yeah. Yeah, you can do it. You can 3D print an actuator. Basically, it's not as good as theirs, but it doesn't cost that much either. A 3D printed actuator, I mean, there's a bunch of them out on Thingy. If you go out and you look for linear actuators, and you can scale them up and down with any kind of motor you want with a screw drive. Now, we have used those in the past with, say, number 8s. And the problem is you always want to have a very coarse screw, so it moves fast. Otherwise, you're spinning your wheels too much to get very little movement. So finding a very coarse screw is important when you're printing your own, but you can do it. We don't use the linears, the purchased ones, because it's just too expensive. We don't have that kind of budget. And we don't need them now. We just don't require them anymore.
Yeah. But the issue we have, I don't know, the woman we are for this end, she has no fingers no more, but she has a palm.
Right.
So the whole gear is his hand. Yeah. So all the motors, electronics should be on the gantry.
Gauntlet.
A gauntlet, yes.
Yeah. And that's all.
Not
that's
to be
all fine.
RoboCup, and she can not become a RoboCup with a lot of motors on.
Yeah. We have found there's actually a study that was done that almost, I believe the number was 92% of people who have upper limb amputations are partial hand. That's a really big number, partial hand. And because of that, that's why we changed our focus. We want to do the partial hand because it seems that is the biggest requirement that we're seeing is partial hand. So we in order to do partial hand, you have to get a lot of your your mechanics have to be inside the hand. Okay, because these partial hands, some of them have some fingers, they have some things that work, and they want to use them. They don't want them covered.
This is our case, yeah.
Yeah. So by making it small enough to where what we do is instead of using this type of a shell, we will actually make a form. And what we'll do is we take the hand and we, of course, the same way you probably do with the alginate, and then we build, of course, the same way you do with making a mold. But we take that mold and we thermoform with a vacuum forming machine over that nub, whatever it is they have that's existing.
Yeah,
And then that is what we use for the hand, and then we put the electronics in there.
this is yeah, but no, for this hand, the hole is for the palm, so there is absolutely no room for any electronic and so on. So it should be on the gauntlet.
That's the whole point that I think you and I are discussing, is there's no one way to do this. You have a lot of people with a lot of different types of injuries.
I'm pleased to meet you, because for the time being, we did not came to the hub and to the group, because we saw that most of the projects were project for robotic hand, where they have no issue with rooms and stuff like that. They put all the mortar in the arms. It's okay, we have to find by ourselves. Now we know that you have the same issue as we have.
It's like the in-move. Remember the in-move hand, and all the mechanics were, the spools and all the stuff were in the forearm. It was terrible.
Which name?
In-move. It's a.
Yeah.
That was
a robotic. It was a robotic project in Japan. And a lot of
time. It was nice in its time.
They have half of the arm, so they can put batteries and motors, electronic, and it's very, very nice. And even for Bionic arm, which is a company, a US company with a lot of fancy stuff like Iron Man and stuff. But
what makes it easy though is by using this methodology with this size form factor we're talking about, we can in fact fit everything right inside the hand on a partial.
So that means that you put the electronic and the motors on the arm, right? On the gauntlet?
No, in the hand, right in the hand. Let me grab my thing again, because you have to remember the one that I showed you earlier with the index gyroscopic technology. This is everything. That's the whole thing.
You were on a stamp on the right of my screen, so I didn't see anything. Yeah. Okay.
Yeah, this is the entire thing. This is the entire thing. Everything, the power, the charger, everything. That's it.
Yeah, but okay.
That's the whole thing.
And how many motors for the full end?
One.
For the
one motor. And it's a very powerful motor.
One motor for 5 fingers?
Yes. And the reason is that's how you get everything down to the size on a partial, and it also makes it modular. And then that one motor, okay, the motor itself is from it's a 3.5 volt motor from a electric screwdriver.
Yeah, I saw that, but could you show me again the full end with
I have a table here full of stuff, and I think I've lost myself a little. Let me see here. I apologize, I'm not very organized. This is the motor here, and the transmission and everything is right here. We use smaller motors if it's inside the hand, but much smaller motors, because by using this configuration, this is the whole motor. The rest of this is transmission, which we don't necessarily need, because you can make your own transmission with the one that I showed you earlier. And then you can put your own gears in. We print our own gears. Now, the reason we do this one is because it's so small, cheap, and it will easily handle the whole hand. Now, in order to do the slips, you know, we use these standard gears. I'm sure you've seen a million times. On your 3D printer.
For my printer.
Yep. And these work very well for the slip. Now, if you want a little better bite, instead of using a cable, you use a belt. And then when it gets to the end of the belt, just like you have on your printer, what will then happen is you just end the belt. You get rid of the teeth on the belt where you want it to stop. So then it's got a really serious grip up until that point. And then you just take the teeth off the belt where you don't want it to have as much of a grip. Now, you'd be surprised how much torque you can really get out of one of these things. You should know. I mean, the gantry on your printer works the same exact way, and it works very well. And what we then do is you can take each finger on a spool, and each finger can have its own belt or its own tendon. So much like the others, when one finger stops, the others keep going because it slips at the grip you have set by the tension.
So okay. So in fact, your fingers, you open the end, or you close the end.
Yep.
But you could not say, I just want to make a pinch between my index and my thumb.
You absolutely could.
You
You always have the option to put in multiple motors. That's the whole point.
yes,
You can put in as many motors as you want.
Yeah, that's what we do here with two motors.
Right.
We have one motor for the index and the thumb.
Yeah.
And one motor for the three other finger.
It's all about the control, though. Now, what we call it index gyroscopics, because it allows you to do the open and close without having anything hooked to your arm. It's all by a gyroscope. Okay, so when I turn my arm this way, it could open. When I close it, and when I turn it this way, it could close. And the speed is determined by how fast I turn my arm. Right now, when you're done, it just quits because you tell it. I mean, and you can have that work with as many fingers as you like. We even had one model where we just powered on and off each finger. So you could actually do gestures, and it made it super non-complicated because it was a simple on-off switch for each finger.
Have you experienced that on a real case with with somebody? Because the lady has our former hand, which was manual. Okay, she's cooking. So she take a bottle, and then she pour the liquid in the vase. Okay, so if the gyroscope understand that she open the hand, the bottle is falling down. So I think that should be quite difficult to understand what to do with the order of the gyroscope.
That's really up to the programming, because the gyroscopics you're doing with programming. So you can actually say, if I do 2 clicks like this, okay, then I want it to give me this gesture. All right. And you can set your gestures up accordingly. And then you can say when the gesture is complete, then it's complete. All right. And it's going to ignore other gestures until you give it one it understands. And by doing that, you don't have anything touching the skin. You don't have the musculars. You don't have the myos. None of all that goes away, which are very much a problem with humidity, with temperature, with your sweating.
You have implemented this software with a microcontroller with an internal IMU, a 6 degrees of freedom IMU.
We're using microbits. And the reason we use microbit controllers, which you guys over in France love, because this was a UK design, the microbit controller has all of that built in. The microbit costs, it used to be before we started having problems with importing, they were running about $25-30. And they actually have a screen, an 8x8 screen. They have all the gyroscopics, they have compasses, they have everything built right in.
And you work with Arduino IDE?
No, Arduino we don't use anymore.
So what kind of IDE is using by Microbit?
Microbit can use they can use blocks, they can use Python, they can use pretty much anything the Arduino can use, but the beauty is you don't have any more hats. The hats tend to go away. Like when you're using Arduinos, you got to have all these hats for everything you want to do. The one I showed you earlier has an Arduino Nano in it, and it's a big pain in the butt.
Look, you see the CPU here.
Yep.
You see, it's a Xiao Japanese. It's 32 bits with an IMU, and now they have a microphone and so on. So it's
this is a microbit. Okay. The whole CPU, everything is in here. It has BLE. It has a screen. You can actually even program this wirelessly through BLE. It has the gyroscopics on it, all built in. It has, it's an amazing little processor, and this thing will run all day on 3 volts.
And you program in Python?
Yeah.
Yeah.
Or some people use blocks, but that's the actual screen there. They light up. Those guys light up. There's an enormous amount of, we use them on, all the little robotic things for test. But the beauty of this thing is that you don't have to have hats. You can add to it. But you've got on here, you've got a BLE antenna, you got microphones, you've got video, you've got everything, and it's cheap. It's very inexpensive. So we switched to this because all our other ones used to be Adreno, and we just couldn't deal with the power requirements. So we got away from it because of power mostly. I mean, you could do anything you want with an Adreno this would do. Of course you can. But it all comes down at the end of the day to how much power do I have to distribute to this individual through the course of a working day. And what do I have to do to make that happen? The reason we switched, it was just cheaper, easier. We don't even have to take the board out of the arm to program it when you want to flash it. It all flashes through BLE.
Yeah, we do OTA as well with this little chip. Yeah. Okay. Oh,
we got it hooked to our Android phones, so we can do things with the Android phones. And so what we're doing is we're trying to keep the circuitry as simple as possible to remove fails. So let's just say you want 5 motors. Okay, somebody just, does it make sense? It's really up to you. But if you want 5 motors, you hook up 5 motors. And what you do is if there's a finger you don't want to use, it's very simple. You could set up one of the indexes or a simple switch. You turn that finger off, now the other ones work. Very simple, and it's a lot less to go wrong. But or you can set up the index gyroscopics to say, oh, I'm going to make this switch, I'm going to do 3 little things. That means the 3rd finger don't work anymore. Yeah. It's just a matter of how much you want to do programmatically versus with switches. Now, all of these things you and I have discussed can be done a million different ways. However, what it comes down to is reliability. And every component adds another level of reliability issues.
I know.
Something that can go wrong. These things, I mean, how wet can that get? Probably not very. We've got this thing in, this thing was being used by a scuba diver, the one I showed you.
We've really?
Yeah.
With the electronic?
Yep.
How do you seal that?
We sealed it. We basically, the processor was in a sandwich bag.
What was what?
A sandwich bag with the processor itself. And what we did is, those little handheld sealers you can buy? You take a standard sandwich bag, and we had all the stuff in there, and you run this little device. It's got a heat element in it, and it seals the bag. And we sealed it around all the wiring. We sealed it around the processor. Everything else we sealed with, yeah, I know, funny, but it works.
Yeah.
And all you got to do is just have a method for the tendoning. And the hand that I showed you with the chain fingers, indestructible. I mean, this thing.
Yeah, no, but I really like the idea because for our hand, we have invented what we call the flexibone.
Yep.
We have a sort of skeleton which go from the palm down to the end of the in one piece, piece, and so on, which is better than the former creation from it was the Kwawu hand.
The Kwawu hand, we've built a lot of those. We've built a lot of them.
So
And one of the biggest things we don't like about it, of course, is I don't like where the fingers connect. So the very first thing we do is we take this all off. And I like the way it builds the hand. I like that it has that look and feel, the Kawau. However, the way the fingers connect is ridiculous. They're going to pull right out of the unit.
we changed that since the very beginning.
Yeah.
We changed
So you
that.
know what I'm talking about.
Huh?
And so you know what I'm talking about. So the
Yeah,
very
yeah,
first thing we do is we replace all of this, and we put the fingers in, and they're connected with bolts.
Yeah.
And the beauty of that is we can take those fingers and put them right in the Kawau hand. Just put them right in, and it works.
My issue with the Kawau end for the time being is the position of the thumb.
Yeah,
The thumb is not at the right place. Is
Right.
not in a position with the index. Is on the side.
And there's no swivel.
So that's why your hand also is interesting with the swivel of the thumb.
Yeah, our point with the Kawau or any of the hands that e-NABLE makes is we're trying to make the finger fit. You know, any of the e-NABLE hands, we want to give people a path to where if they don't want the existing finger technology and they need a lot more strength, you know, where they really want to lift poundage, that it can attach. So the Kawau is a nice build. I like the Kawau cuff, you know, the most. And version 3 of the Kawau now has a really nice wrist. The wrist on the new Kawau is really nice. It's a push button index wrist. It's very, very nice. Much nicer than the version 2.
But the Kawau is made for people without palm.
Yeah.
Yeah,
And
but in my case, we want, in our case, we want to build a prosthetic for people with a palm. But if the people have no arm, it's better. But we want to be with a palm.
I understand. And
that's a lot more complicated. That's a lot more complicated. But this is the goal, because
and our goal is similar, because we want to do just when people have partial hand. That's our focus.
Yeah. If you want to see what we've done, because we have a website which is partially in English, and we also use students to help us. So I give you the website and my email, and I would like to get your direct email, just because I'm sure that we have we have things where we can learn from you. So I just send you.
Everyone can learn from everybody. That's the whole point.
Yeah.
And I'll give you also. Let's see. I'm trying to find my.
Patrick.
I'm trying to find my chat. Here it is. I'm going to go ahead and send you mine. Oh, I've been to your site. Yes, I've been to your site.
You've been?
Yeah.
Okay. So we try
I recognize that hand.
This one is not yet on the. This one is the last one. Is not yet on the website, because I am quite lazy to write. So it's a long job to write what we've done, so on. So
I think the whole point of this discussion is there's no one way to do anything. I think the point you need to, that people need to accept is we need to try to make a way to take these good ideas that people have and find a way to make them fit all the different products that e-NABLE has, so everyone can take advantage of it depending upon what type of injury they have.
I'm not using Facebook. I'm 100% against Facebook. So don't you have an email? No, it's awful for me. Facebook may be very interesting,
but that's all right.
It's so much used by crazy people that Mr. Zuckerberg, I don't want to do anything with it.
How about that? I'll just give you my e-NABLE email.
Yes, well, okay, Rick. Voilà. You see, I'm Patrick at Grenoble, and you are Rick at the.
Yeah, I've been to your site. You guys were originally making some interesting mods to the Kawau a while back. I know you changed the wrist around a lot, and I like, you did some really nice stuff.
and we are doing what the customer needs right now.
Exactly.
We are doing few hands and a lot of very special tools dedicated to eat, to make ski. We have a lot of little boys and girls who want to go skiing without one hand and so on. So we have a lot of job in that part.
I understand. If you don't mind, I see we just got Jeremy here, and one of the things I want to do, if you don't mind, is I want to make sure I share my screen again, because I want
Yes.
Jeremy to see this. Jeremy, this is what we showed earlier. This document from RealPars. It's really a worthwhile read. And also, I have another one here, and I don't know that we got to this one or not. Oops, now I've done it. This thing is in my way and I can't see. Really?
Sarah, is it fair to assume that you'll help us capture these links that he's showing, and when we share the video, those links will be in there, right?
Let's see here. This is another one.
I haven't copied the websites, but Rick, if you want to share the website links to the chat, I can add
Sure,
them
yeah.
to the post in the meeting. And I actually have to leave now, but
It'll be
this
in the
has
save
been-
chat then, yeah.
this has
I'll
been
just drop them in there.
this has been a great hour, and if you all want to keep talking, I can pass hosting over to someone.
I wouldn't mind if you want to keep going, I'm fine. But what I wanted to make sure is that you guys just knew about these sites and that you had access to them, because it really goes through, I think, on a really nice, simplistic level, what each of the different kinds do and why would you use one versus another. And I looked around last night for something, and this is probably these are probably one of the best things I found. This one here, the RealPars guys, I think they just did it.
Rick, do me a favor. Just I know Sarah has to go. Do a follow-up email to her with those links, just so she can. I know she needs to drop out and go to another.
I just put them in the chat.
I copied them from the chat.
Okay,
Yeah.
so you can take off, Sarah, if you want to make me host. We're going to be wrapping up here. Rick, I wanted to apologize because I had this on my calendar as 1 p.m. Eastern, and so I thought I was joining here at the beginning of the meeting. I guess it shifted back an hour. So
Oh no, it's all right.
I'll have to go check the recording.
Patrick and I have been having a lot of fun. So
okay, great. Well, I'll look at the recording. I'm sure there's a lot of good info, but if you guys want to continue, you're welcome to. But since I'm at the tail end here, I think I'm going to go ahead and drop back out because I want to kind of see the whole thing from the beginning. So I'll go watch the recording.
Patrick, let's see. Hold on. Do you want to continue, or have you had about enough of me today?
Oh, I have plenty of time